Welcome to Climate Conversations. I'm Clare Nasir. In this show, we're exploring a fascinating part of climate science, how melting sea ice across the Arctic Ocean might be reshaping the winters we experience here in the UK and Ireland. This year, the Arctic set yet another troubling milestone. March 2025 saw the lowest winter sea ice maximum in the 47-year satellite record. But this isn't a distant problem. New research reveals that the competition between Arctic sea ice loss and ocean warming creates a tug-of-war that could alter our winter weather patterns here in the UK and Ireland. Here's what makes this story so compelling. Earth's climate system doesn't change uniformly. The Arctic has warmed at least 3 times as fast as the global average, something scientists call Arctic amplification. These systems, however, do not operate in isolation. The atmosphere connects everything. What happens at the pole ripples outward, touching weather patterns thousands of miles away. For us, perched on the western fringe of Europe, this matters enormously. We sit exposed to the North Atlantic, where Arctic changes meet ocean currents and the jet stream, both that govern our weather and climate. On a basic level, the temperature difference between the Arctic and the tropics determines the shape, position and strength of the jet stream, and this in turn affects our own weather outcomes. But here's where it gets complex. While the Arctic warms rapidly, the tropics are warming too. Climate model projections show us something remarkable. These two warming patterns pull the jet stream in opposite directions. Arctic amplification wants to shift our weather systems one way, tropical and ocean warming wants to shift them another. It's this tug of war that makes projecting our future winters so challenging. The winner of this battle will determine whether our storms track north or south, whether they strengthen or weaken, and ultimately what kind of future winters we will experience. Diving deeper, there are many more dynamics that interact, and understanding how they influence and feed into the UK's seasonal winter climate is crucial in preparing for our changing winter climate. Today, Burkill talks to 2 scientists at the forefront of this research. They have published groundbreaking analysis on how Arctic sea ice loss might affect British and Irish winters. So here's Alex talking to Dr. Ed Blockley from the Met Office, an Arctic sea ice expert, and lead author Dr. Steph Hay from the University of Exeter.
Ed, Steph, thank you so much for joining us on Climate Conversations. Really fascinating paper that you've been a big part of. But before we get into it, Ed, let's look at the bigger picture and get some sort of understanding. Now, when it comes to Arctic sea ice, just how quickly is it melting? How quickly is it disappearing?
So since satellite records began in the late 1970s, we've observed a loss of Arctic sea ice throughout the season. The largest loss is at the end of summer, in September into October, when we've seen on average a loss of about 80,000 square kilometres per year, which is an area about 4 times the size of Wales. So it's been quite a significant loss of Arctic sea ice that we have observed.
That's a remarkable rate of loss, and so no wonder, I guess that's been the driver behind you looking into this in such a passionate way. But in terms of the weather that they usually get in this type of region, what kind of weather do they normally get, and is that changing as a result of the decline in sea ice?
The Arctic is characterised by cold weather. I mean, it's completely dark in winter.
Of course.
And light in summer, but it's long, cold, dark winters and generally cool summers. The Arctic has, but the Arctic is warming, and it's warming at least 3 times the global average, and so we are seeing changes there. And one particular change we see is that there's now a lot more rain in the Arctic as the sea ice is declining, and less snow. So more often the precipitation is falling as rain, which makes quite a difference to things.
And is that then contributing to the rate of sea ice melt?
Like rain on snow events on the ice can help melt the overlaying insulating layer of snow on top of the ice and expose it to the air. Is that true?
Yes, well, yes, it depends on the time of year. So if you get rain on the snow in winter, what happens is you reduce the thermal conductivity, increase the thermal conductivity of the whole of the whole system because the snow is quite insulating. So then you actually grow more ice at the base of it.
So it's quite a complicated thing. So that's why there's so much work that has to go into it.
Increase in rainfall has other implications for people that live in the Arctic, particularly for reindeer herders, for example, because the reindeer quite often will move the snow on the ground out of the way so they can eat their little bits of lichen and stuff. But if rain falls on it, then you get like an ice layer that's set solid, and they then can't access their food sometimes. So there are some real human implications of these changes that we see in the Arctic.
Away from the Arctic itself, can you go into some of the mechanisms that the changes that you've discussed happening within the Arctic then influence other areas, particularly towards the UK?
Yeah, so the one mechanism by which Arctic changes could have a wider influence is through changes in the jet stream. So the jet stream is a major driver of weather and climate in the whole northern hemisphere, and it's partly driven by the difference in temperature between the equator and the Arctic and the poles generally. And as the Arctic is warming faster than the global average, what's happening is that gradient is reducing, and that could have implications for the jet stream as far as the location and the strength of the jet stream, which could then impact our weather and climate in mid-latitude regions.
So it's more likely that the jet would shift a little bit further southwards looking at this. But there are lots of other things at play. Is it fair to say there's a sort of tug-of-war between all the mechanisms working some against, some for each other in terms of how it's going to impact the UK and Ireland as we go through our winters?
There are lots of competing changes around the globe. We have Arctic warming, we have tropical warming, and the relative magnitude of those will determine how the gradient looks between the equator and the poles, which will then impact the jet stream and other things.
So it's really complicated. No wonder it's like your research is so important and has helped understand some of it. Steph, before you got onto this paper, onto your research, what did you already know about how changes to Arctic sea ice were affecting the UK?
There had been increasing evidence in the research over the last 5 to 10 years that Arctic sea ice loss can cause a small but significant change to things like the jet stream and the storm tracks. What was less obvious was how large that change would be compared to some of the other competing effects, and how that might manifest regionally for an area like the UK and Ireland.
You touched on how the changes to Arctic sea ice could help shift the jet stream further south, and it may decrease its strength depending on lots of various other things. But how else could that influence our weather with a weakening jet? Does that mean the likelihood of blocking highs becoming greater?
So it's not all that clear what happens to the strength of the jet. Well, it does shift. That's become quite clear in the research. Even in our paper, we found that the models didn't necessarily agree on what would happen to the strength of the jet. In terms of blocking highs, I'm actually doing research on this right now. I'm working on Greenland blocking, and the models have struggled to represent this sort of the sort of large timescale variability that we have in Greenland blocking. But they're all in very good agreement that we would actually expect less blocking into the future, despite this sort of potential chance that the jet might be moving a bit slower. What's sort of interesting is that blocking can create sort of extreme conditions by making stagnant weather over certain regions. And we still expect the same sort of effects that would happen from blocking to occur, even though we have less blocking into the future. So if you look at the model and you look at the sort of like heat spells or cold spells over the region, they don't decrease because we have less blocking.
And why is that?
I don't think that it's all that clear yet,
You knew that question was coming.
Yeah, it's what people have found so far, but it's not all that clear why that's occurring. And there's certainly some concern that we're missing processes that are important to developing blocking. That's why the models haven't done all that well at representing it in the present day.
Ed, do you anything to add on that one?
No,
Okay.
not on that one. I'm a sea ice guy.
That's fine.
Steph's very dynamics is
Absolutely
more.
fine.
But what's been made clear in Steph's paper is this tug-of-war, which is the ratio of essentially global warming to Arctic warming and the Arctic sea ice. And it's understanding what that magnitude is something that we're working on. So it's been shown that the recent climate models probably underestimate that, so that we don't get enough sea ice loss per degree of global warming.
So it's clearly quite complex, but why is it so important to try and understand the changes, the mechanisms that are going to influence the UK?
Some of our past work has shown that the Atlantic is a bit unique in how the tug-of-war takes effect here, in that the changes in the Arctic will cause the jet to shift towards the tropics, but changes elsewhere would cause the jet to shift more towards the pole. And where we are located here means that we would really see these effects, and really small changes in the location of the jet stream and the storm tracks can have large differences in, say, a storm passing directly over the UK or diverting to the north or to the south and not impacting us.
So small changes, when you look at it on the big scale, can actually be really big changes when it comes to the UK, which is what we find with weather constantly. But when you take it even further with climate, then it kind of amplifies it in many ways. Now, with your research, with this paper, what did you find most surprising? Was there anything that surprised you?
I think there were a couple things that were surprising about it. And one of them is that a lot of the sort of average changes that we found were relatively still quite small in keeping with previous research. But we looked into some of the more extreme changes as well. So, for example, we found that there'd be a small decrease in the number of storms that might impact the region in response to sea ice loss, about 1% average. But that would actually be a 10% change in the number of strongest storms impacting the region.
So fewer storms in general, and the really strong ones
Would decrease by even more.
which from many people's point of view seems like a positive thing. I don't think many people want the stormy weather. It gives us things to talk about and keeps us very busy, but it can also be hugely impactful. But as we were talking with Ed, there are other drivers that might be leading to storms increasing in intensity, isn't there?
Exactly. So it doesn't happen in isolation, Arctic sea ice loss. It's happening at the same time as all these other changes are occurring. What we found is that for our current best estimate, the effect of sea ice loss will be almost exactly balanced by the effect of the other changes. And so understanding the relative amount of sea ice loss that occurs compared to the amount of global warming could change these projections in quite appreciable ways.
You've already touched on the change in storm frequency, particularly the stronger storms as a result of the reduction in Arctic sea ice. But what were your top conclusions from your research?
One of our main conclusions is that the size of the changes we might expect in response to the changing Arctic are of the same size that we would expect from general greenhouse warming, but often opposite in sign. Where that isn't true is in the temperature response, where the effect of Arctic sea ice loss on the temperature of this region is very small compared to the general warming we'd expect from increasing CO2.
So around the UK, we're seeing our temperatures rising, and although Arctic sea ice loss would reduce that, it's not anywhere near, or it's not enough to counter the amount that we're seeing temperatures rise for other reasons.
We don't think it would reduce the temperatures for the region, but there's quite a lot of model spread on this. So any changes, though, would be so small that they aren't really, it's not a dominant driver into the future.
What are your next steps? Now you've carried out this research, you've written this paper. Where do we go from here?
We were somewhat limited in this research by the relatively coarse resolution of climate models, which are much more coarse than something like a weather prediction model. But the newer generation of climate models that are coming out generally increase the resolution. This helps us to represent processes on a smaller scale, so that we might have be able to simulate things like mid-latitude storms much better at a higher resolution. So we would like to see that these results hold when we increase the resolution. This would also allow a more detailed understanding of the regional changes of something like sea ice loss.
Are there any other things that we could do, or in an ideal world, what could you do differently to get better understanding?
It's kind of a hard question. So a lot of this research that I presented in the paper comes out of some work where we coordinated experiments across many models. And so this has been our best attempt to date to really understand if there's any differences in the way that the models simulate these changes to Arctic sea ice loss. So this required many, many years of simulation, like thousands of years of simulation, which sort of required us to be at this low resolution for the models. There's been questions going forward about the utility of running these again in the next generation of models, if we feel like we've gotten to a pretty solid understanding, actually, with the project as it went. So there's been questions, do we have another version of this model intercomparison project, or do we say that we feel like we understand it pretty well at this point? As far as I know, the only real work going forward on this at the moment is towards increasing the resolution, but it's actually sort of to understand a slightly different problem, and which has to do with, we think that it's possible the models are actually underestimating some of the forced response, and that might be improved by increasing the resolution.
Where do you both stand when it comes to use of artificial intelligence in terms of studies like this and other climate studies?
Artificial intelligence is showing some very promising results for certainly for short-range forecasting and for interpretation of observations, where it's very much looking for patterns in the data. With climate projection, things are a little bit more complicated, because we would need to be confident that the relationships that AI methods are finding are still valid in future. So I think there's still a place for physical-based models and scientific understanding, but I'm quite excited about the sort of blend between using AI techniques with the traditional physical modelling and scientific understanding to try and constrain our projections of future Arctic sea ice, for example.
So you can see the benefits, but you have to be careful.
Yes, the problem with climate modelling is it's very hard to verify what the outputs are, because we don't have a time machine, and so one has to be a bit more careful about verifying and validating what model is telling us, whether that's an AI model or a physical model. But I think there's a place for a joined-up approach there.
And Ed, what's your next step?
We're briefing government as to what the science is telling us about how Arctic sea ice loss might impact UK weather. There's been a lot of speculation about this question over the last, maybe decade or so. And so this is an important addition to that piece. And also this is the first study that's really focused on the UK and Ireland itself, rather than just looking at mid-latitude. So this is a piece of work that we have been part of to try and provide more measured guidance to government on what might happen in future, and how Arctic sea ice might impact our weather.
Thanks so much, Ed and Steph. It's been a real joy talking to you. I can just see how much knowledge you have about this, and it's really fascinating. I'd love to talk to you for longer, but thank you so much for coming in.
Thank you.
Thanks for having us.
Our thanks to Dr. Ed Blockley and Dr. Steph Hay for their time and scientific insights. The full research paper, The Impact of Arctic Sea Ice Loss on Winter Weather in the British Isles, is published in the Royal Meteorological Society's quarterly journal. You'll find links to the paper and additional resources on the Met Office website. There are more climate conversations in this series. Check them out on our YouTube channel. And Alex and I will see you again soon.